All right, so we're looking back here at chapter 12, some of the homework questions people were curious about. So I've got 43, 50, and 70, and we'll at least get them set up. We may not go the whole way, but we'll at least get them set up so we can see what we're doing. So hopefully y'all can see my screen, and here's number 43. It says we've got a uniform trapdoor. So uniform is going to tell us that the mass is evenly distributed. We don't have to worry about anything funky there. So it's uniform. It's 1 meter by 1.5 meter, weighs 300 newtons. It's supported by a single hinge and by a light rope tied between the middle of the door and the floor. So that's that rope right there. And we got the hinge. The door is held at the position shown, where its slab makes a 30-degree angle at the horizontal floor, and the rope makes a 20-degree angle with the floor. So find the tension in the rope and the force in the hinge. All right. So let me reproduce that picture on the whiteboard, and then we'll go to the whiteboard and see if we can figure that out. So what are we going to want to do in general, though, guys? What's the process going to be here?
Find the forces on the trapdoor and in the rope so that they're at equilibrium and the trapdoor isn't moving.
Okay, yeah, that's exactly it. We're going to want to see if we can figure out the equilibrium, which means we need to balance forces and torques. So this is a little bit different than before, because up to this point, before rotation, we just would have gone with forces, but now we need to deal with torques as well. Okay, so I think I got everything here. Let's go to the whiteboard.
Okay, sounds good. But it's no glue.
All right.
Oh, and it's only 2 ingredients.
So I'm going to mute everybody real quick. If you want to come back in and ask me a question, feel free. I'll be happy to answer them. Just, we're getting some background noise. Okay, so here's our picture. So let's start by just thinking about what forces are acting on this. So what are the forces acting on the door?
Gravity.
All right, we got gravity.
The force of tension from the string.
Okay, the string. Can you think of any others?
Torque.
So torques are not forces. We will have to worry about the torque in a minute, but let's just think forces.
The force from the hinge.
Okay, there's also force from the hinge. Let me draw this picture kind of from the side. Okay, here's the door. So we've got gravity that's pulling it down. There's the tension, which is over to the side here. So let's call that tension. But there has to be something else. Because if you look at this, there aren't enough forces to balance. There has to be another force, something that's pointing upward to counter the downward tension and gravity. But that force also has to be pointing a little bit to the left to counter the right hand pull of that tension. And so you guys would have called this a normal force back in the day. And it still is a normal force, but it's going to be happening at the hinge. And so I'm going to call that, let's kind of go this direction. I'm going to call it H. So that's the force that's happening at the hinge. So how do we feel about those forces? Okay. Well, that's what we've got. So we need to balance these things out, and then we also need to balance out the torques. So I'm going to suggest that we do these two separate problems, kind of do a force diagram where all those forces are emanating from the same point, because that will help us figure out components. And then we go to the torque question, which will be from this picture right here. All right, so here's the force diagram. So here's our door. Everything looks like a block. But I've got gravity pointing straight down. I've got this tension force. But what I know about this tension force is that there's an angle of 20 degrees. They told us it was 20 degrees from the floor up, which means it's 20 degrees from the horizontal down. And then there's the hinge force. I know absolutely nothing about it, except that it's pointing this general direction. So let's break everything into components. So gravity, it's just going to be the weight pointing down. Shoot. Anybody remember how much it weighed?
300 newtons.
300 newtons, thank you. So that's going to be 0 minus 300 because it's pointing straight down. So in terms of the tension, if we call that guy big T and we need the components, we can break it into sines and cosines. So the horizontal bit is going to be a T cosine of 20 degrees. So here's T, it's going to be T cosine of 20. And then the Y is going to be minus T sine of 20. So that's just from the geometry of that picture. So then I know H is just going to have to point in the opposite direction. So H is opposite direction of the sum of these. So H is going to be negative T cosine 20, and then 300 plus T sine of 20. Because I need those three to add up to 0. So how are we doing with that piece? The part that just comes from looking at the force diagram. You buy it? Thumbs up? Okay, getting lots of thumbs up. Cool. All right, so there's the balance of the forces. But now we need to look at the balance of the torques. So what we need to do is pick a place about which we're rotating. It doesn't actually matter, but we should definitely pick something that, or a location where we have forces coming out. Right? Because if the forces are acting at the point of rotation, we know they give us 0 torque. So that really suggests one of two places. Either at the hinge or at the center of mass. Which one do you want to pick? Doesn't matter.
The center of mass?
Okay, I agree with you, Max. I want to pick the center of mass. It doesn't matter. We can pick anywhere. And I know you might be thinking, right, but it rotates about the hinge. Well, that's true. But if we go through the center of mass, then two of our vectors create 0 torque, which I definitely like. So let's do that. Let's look at the torque that's happening through that center of mass. All right, so let me do this up here. I'm going to erase my picture, which is probably dangerous, but no, I'll reproduce it. 1.5. I think that's really all that we care about right now. 30 degrees. All right. So in terms of about the center of mass, if we look at our torques, gravity is going to produce 0 newton meters of torque, as is tension. All right. But that leaves just the H going about the hinge. We got ourselves a little bit of a problem. What's wrong with doing it this way?
We need to know the force in order to find the torque caused by the hinge.
We definitely need that. But that's not really the problem. Think about it. Gravity is producing no torque there. Tension's producing no torque. So there's only torque from this hinge force. What should happen if that's the only thing?
It won't be in equilibrium anymore.
Right. And kind of Victor hinted at this in what he typed. He wrote, it should, because it should be 0. And I think what he's saying is that the torque, sum of torque needs to be 0. So the problem is we can't actually go about that point. That's not going to work for us. So let's go back to the actual place where we're rotating. And now think about this. The H is not going to do anything. It's not going to produce torque. But we're going to have gravity and we're going to have tension. But those two are trying to rotate in different ways. Gravity's trying to make it go around counterclockwise. Tension's trying to make it go around clockwise. And those will cancel each other out. So let's not go to center of mass. Let's go to the torque around the hinge. Because now we can get these. So we have to know how far away those forces are being applied. And then we need to know the angle between that radial arm and the force itself. So if we look first at how far away they are from each other, they're just the distance from the end of the door to the middle of the door, which I think from our picture is 0.75 meters. So if we go to gravity, let's do the torque due to gravity first. It's going to be the size of the force, which was 300 newtons. That's going to be multiplied by the distance away. So that's 0.75 meters. And then we need the sine of the angle in between them. So on my picture, the radial arm is this that I'm kind of making thick and dark. So I need to know the angle between gravity and that. So what is that?
We have 20, that's 90, 70?
Not 70.
Oh, wait.
You're on the right track, but you used the wrong initial angle when you started calculating.
30? So 60? Use
It's going to
30
be
instead.
60 degrees
Yeah.
because we knew that the slope of this thing was 30 degrees.
Oh, yeah.
So then the other angle is going to be 60. And we can either make that positive or negative. We just have to make sure that once we choose what sign that has, that the other one has the equivalent but opposite. But let's just get the magnitude. So these are all numbers that we can calculate, and that'll get us the torque due to gravity. Now, this has to be balanced by the torque due to the tension. So let's think of the torque due to tension. It's going to be the magnitude of that tension force, which again, we don't know. So that'll be an unknown T. That's what I was using down here, so we'll use big T. We need to know how far away it is from the point of rotation, which is that same 0.75. But then we need the sine of the angle in between those two, which is going to be, let me erase the H here, clean this up a little bit. I need to know that angle right there.
10 degrees, right?
So 10 degrees. What do you guys think? Does that sound right? How'd you get that, Jacob?
Subtracting the angle of the hinge and the angle of the strings, so 30 minus 20.
Okay, so we knew that this one was 20 degrees. You can do however you want to use the geometry there. Use the fact that this one's 150 because of the fact that it makes a straight angle. So then that's 170, leaves us 10. Or, I don't know if you remember this, but if you want to know the sum of two angles, it's actually equal to the exterior angle of the one opposite. So those two have to add up to 30. But regardless, it's going to end up being 10 degrees. So there are the torques due to those two forces. But since this is an equilibrium, those have to balance. So we're going to get 300 times 0.75 times sine of 60 needs to equal T times 0.75 times sine of 10. So we can solve this for T. We're going to get 300 sine 60 over the sine of 10. And that's going to equal our tension force. So balancing the torques gives us this for our tension. And then what we can do is we can take that and put that into your H to figure out how big H needs to be. And I'm just going to look back here real quick. It just says find the tension in the rope and the force at the hinge. So those will give us our two numbers. All right, so any questions on how I did that? All right. So there's number 43, or at least the big shove to get you where you need to be. All right, so let me share my screen again, and then we'll go look at the next one. All right, so number 50 down here somewhere. Let's see. Okay, So it says a disc between vertebrae and the spine is subject to a shearing force of 600 newtons. Find its shear deformation using the shear modulus of 1 times 10 to the 9th newton per meter squared. The disc is equivalent to a solid cylinder, 0.7 centimeters high and 4 centimeters in diameter. All right, well, let me draw the picture first. Get all this information on the board, and then we'll go to the board. So it's 0.7 centimeters high and 4 centimeter in diameter. We've got the force of 600 newtons. And we've got a modulus of 1 times 10 to the 9th. And we want to find deformation. All right. Okay, so I'm going to stop sharing and we're going to go to the board. Okay, so I got our picture here. We've got the cylinder and we're applying a shear force. So what does that mean again? What's a shear force do?
Compressing.
It's not compress. Okay, so like scissors is what Victor says. Eduardo says it shifts. So this is the force that's parallel to the surface. So it'd be like we're taking the top of that cylinder and we're pushing it to the side. So what we're going to see when we apply that force is that cylinder now looks like this, because we've applied that 600 Newton force on the side. Okay, so this is our picture. This is what's going on. All right, now the shear modulus. How do we calculate a modulus, whether it's a shear or a tensile or whatever? How do you calculate modulus?
Mm-hmm.
So Eduardo just put F divided by A times L. That's a specific one of them. How about just in general? What does it mean when we look at modulus? Well, how about this? We have stress and strain. Oh, Jesus just put that in there. Okay, it's stress over strain. That's how we always calculate our modulus. So what was stress? Okay, so Victor just put in the chat, it's force per area. So we need to know the force per area to get our stress. And then what's strain? Okay, so Victor just put, that's the deformation, right? So when we calculate, if we want to find one of those, that's how we're going to use the modulus. So our modulus is stress over strain, which is going to be force per area. And then the strain, it really depends what we're looking at in terms of the strain. When it was tensile, strain, so like pulling, it was the change in length over the original length. But for stress, you may remember that it comes to the angle. It's, if we were to look at this angle right here, the strain, we actually calculate that as the tangent of that angle. Or if you want, you can think of it as a x over L kind of deal. So we know the modulus. We're given that number, 1 times 10 to the 9 Newton per square meter. The stress we can actually calculate. Since stress is force per area, we know the force was 600 newtons, but over what area is that applying? Maybe not even in terms of numbers, but like what shape area are we going over?
Yeah. I can't tell if it's supposed to be like, where's the force like impacting? I don't know. Does that matter even?
Impacting like circles?
Okay,
Yeah,
so
like
it's going over the top. Think of it as going
over the top. Oh, okay. So yeah, pi r squared.
It's that cross-sectional area of the top. So like Eduardo put that up there, pi r squared. Jacob, you're right. It's pi r squared. And so we're really looking at the area of that top surface because that's where the force is being applied. So that's going to be pi times 0.02 squared. It's 0.02 because we got to convert from centimeters to meters. And remember that 4 centimeters was the diameter. So that's actually a 0.02. So that then even tells us we can solve this for tangent of theta. It's going to be that stress divided by the shear modulus. And notice that the units here, they're going to cancel. This is going to be dimensionless, which is what we expect for tangent. The trig functions, they should always be dimensionless. And that would actually be enough, I think, to answer the what's the deformation. You can say, well, it gets pushed off at whatever angle. If specifically, and this is where you got to kind of be careful, because if you go and you check like the back of the book or a solutions manual or something, they may ask you to figure out what that x is. So if tangent of theta is not enough, how could we figure out what x is?
Yeah, what Victor said. Sine of theta times the height of the cylinder.
Okay, so we know that this unknown is our opposite. And then Victor said use sine, and Jacob backed him up, that this is actually 0.7. And I think you're not going to be right. Because think about what happened. When it was originally just in place, its height was 0.7 centimeters. As we've produced that shear, we've actually stretched out the length of that side.
Yeah.
So it turns out that this 0.7 is this vertical side right there. So it's actually going to be tangent. So this whole tangent of theta, this is actually equal to x over 0.7 centimeters So if you were to take whatever this number that we just calculated was and multiply it by 0.7, that will tell you how many centimeters this thing moved across the top. My guess, I mean, I haven't done the numbers on these, but my guess is that it's going to be quite small because your vertebrae don't exactly deform that much. At least they shouldn't deform that much. So I'm just running the number here real quick to find out what the tangent of theta is. So I'm doing this calculation right here. And so I got that the tangent of theta is 0.0004774, yada, yada, yada. Which then if I multiply by the 0.7 centimeters, that gives me that my x is 3.3 times 10 to the minus 4 centimeters, not meters, centimeters. So we're talking 10 to the minus 6 meters, which is microns. So it moves only 3.3 microns over, which is really small. And if you were to go back to this right triangle, what you're going to see is that this angled side is virtually the same as 0.7. If you use the Pythagorean theorem. In fact, let me use the calculator again for that. So we're going to have 0.7 squared plus this tiny ass number squared. So what my calculator gives me is that this diagonal length is 0.700000008. So we've increased it by 0.0000008 centimeters in length, which is virtually none. So if we go back to the, could you have used sine? Yeah, sine would have given you pretty much the equivalent. So if you'd done inverse tangent of this, and then taken the sine of that times 0.7, you'd still get something that's pretty much equivalent to 3.3 times 10 to the minus 4 centimeters. All right, so again, in terms of what answer we're giving, well, it's how do we actually want to measure deformation? What do we want to show that? If it's how far over linearly did it go, that's that x. If it's what angle did we bend, it's this thing right here. And well, the inverse tangent of this, which is going to be pretty much that because of the small angle approximation. But both of those are a measure of deformation. So just remember what shear does. Shear is a force that's going parallel to a surface. It's basically dragging that surface. Think about the top of this vertebra. It's being pulled over because that force is going parallel to the surface, as opposed to coming in perpendicularly, which would compress it. Or if we pulled it up, right, where we're using tensile stuff. But the key is right here. Modulus is stress over strain. So the stress is the measure of force. So the force per area or force per volume or whatever it happens to be. And then strain is your deformation. All right, so is that better for 70? Any questions now? All right, hearing none, let's go take a look at number 70. All right, so number 70. A pencil rests against a corner as shown below. So that's this figure right here. The sharpened end of the pencil touches a smooth vertical surface, and the eraser end touches a rough horizontal floor. So I'm already interpreting this as the vertical surface has no friction, and the horizontal floor will. The coefficient of static friction between the eraser and the floor is 0.8. The center of mass of the pencil is located 9 centimeters from the tip of the eraser and 11 centimeters from the tip of the pencil lead. Find the minimum angle theta for which the pencil does not slip. All right, so let me draw the picture again. But this is going to be similar to the first problem where we need to balance forces and we need to balance torques because we want this to be in equilibrium. So let me just draw this picture here. We've got a theta we're trying to find. The center of mass is 9 centimeters from one end and 11 centimeters from the other. And then the other piece of information that matters is the mu. And that was 0.8. Okay, so I got everything on the board, so let me switch to that view. All right, so here's our picture. And let's do the same thing as we've done before, which is break down the forces and figure out what kind of torque we need in order to keep this thing from falling. All right, so let's just start with forces acting on this. What do we got? All right. As always, Victor went ahead and gave us the two always. Gravity and normal. I actually brought you up in my other class, Victor, because we were talking about a force diagram. I joked about how gravity is always there, and you're the first one to always bring it up. But okay, so we've got a gravity, we've got a normal, and I'm going to guess what you mean by normal, Victor, is the floor. Ralph says there's a wall, and there is going to be a force at the wall. And then there's also a frictional force. Okay, so let's draw all those forces. So just a force diagram, not worrying about where they are right now. So we've got gravity. We've got a normal. We've got friction. Which way is friction pointing?
To the right, like x-axis direction.
Okay, so it's going to be pointing to the right because the bottom of the eraser is trying to move to the left. So the frictional force is moving to the right. And then there's also the force of the wall. So we've got gravity, normal, and friction all, no, gravity's not down there, I lied. Gravity's actually at the center of mass. And then there's the wall force, which is over here. And which way does that point? So Victor just said to the left. Do you guys agree?
It's not that I disagree, it's just I don't think it points in any direction.
Well, it definitely has to have a leftness to it. Because if you just look at these three forces right now, this would suggest that it needs to move to the right. But it's not moving to the right. Or sorry, to the left. No, yeah, right. So confused. This would want to move to the right, but it's not moving, which means there does have to be something that points towards the left, but it also could be pointing up or down a little bit, depending upon how n and gravity work out. So I don't know exactly where it is, but just for the sake of having something, I'm going to put it there, and I'm going to call it W for my wall. All right, so are we good with that? At least the forces. All right, so I see a couple of thumbs up. Thank you. Okay, so let's go to the normal. Or not normal, I'm sorry, the torque. So let's go to torque. So what about the torque? Well, let's go about the point of rotation, which is basically the bottom of the pencil. So the normal force and the frictional force are going to do nothing, but gravity and the wall force will. So let's start with gravity. So for the gravity torque, so tau sub g for gravity, it's going to be the magnitude of the gravity. So that's the weight of the pencil. Did they tell us that? I'm going back and looking here real quick.
I don't think
they do
so.
not. Okay, so it's
Yeah, no, they didn't.
some unknown weight. So let's just call it mg times its distance away, which is 9 centimeters. I'm going to leave it as centimeters because converting them all to meters will not change anything here. It will give us our torque units in Newton meters. Mine are going to be in Newton centimeters, but they still are going to have to balance. All right, so that's the torque due to gravity. So what about the torque due to the wall? Well, the torque due to the wall is going to have to equal this. But if we think about it, it's going to be whatever its magnitude is.
Wait, don't we need the sine of theta for the torque of gravity?
Oh, yeah.
Or...
Thank you. So we need the sine of the angle in between them. And what's that going to be?
90 minus theta? Or theta minus 90? I don't know. 90 minus theta sounds more right.
It's going to be one of those. Yeah, it's going to be 90 minus theta, 90 degrees minus theta, or pi over 2 minus theta.
Or the absolute value, I guess.
And just because.
Theta minus 90.
Do that one. But you know what? I'm going to do something else with that real quick. So this is going to be 9 mg cosine of theta. Just using the fact that I know sine and cosine are related that way from trig. All right, so there's our torque due to gravity. But thank you for that, Jacob. I did totally forget to put that in there, and it's super important. All right, so let's think about the torque due to the wall. So I need its magnitude. Okay. We kind of need to figure out from this force picture where the wall is actually pushing against this. Okay, so let's just think of like a force diagram here. So the wall is getting pushed against by the pencil. And then it's pushing against the pencil with an equivalent amount. So the question is, where does this really point? Well, it actually does point straight left. Because think about it this way. Think about this point on the pencil. Let's say this started rotating. Let's say there was no wall, right? If there was no wall, what would happen to the pencil?
It would fall flat.
Oh,
It would fall, it would rotate so that it was flat, right? So it's rotating, but it's not actually changing its position up and down. Like this point on the eraser is still going to be where it is if there were no wall. So there would be no vertical motion, which means this normal force actually is canceling the weight of the pencil. So if these two are undoing each other, now as soon as we put in a wall, it doesn't change anything in terms of that verticalness. So that means that that wall force is actually the same as the frictional force. So I'm going to write this, that the torque of the wall is actually equal to the frictional force times its distance away, which is 11 centimeters, times the sine of the angle. Ooh, I lied. It is not 11 centimeters. What should that actually be?
20.
20. Because it's only 11 centimeters to the center of mass, but another 9 to the point about which we're rotating. So we've got our frictional force times the 20 centimeters times the sine of the angle in between them. Okay, so what is the sine of the angle between the wall force and the radial arm?
Theta.
Yeah, so that is theta, good old alternate interior on parallel lines or whatever. So we're there. Now the frictional force, we know that that's actually equal to the normal force times mu. So that's going to be 0.8 times the normal force. But the normal force is actually to the weight of the pencil. So they're equal. So that's going to be another m times g. So there's the torque due to the wall. It's actually equal to 0.8 mg times 20 sine of theta. So now let's balance those torques. We're just going to set those equal to each other. So we get 9 mg cosine theta equals 1.6, or no, 16 mg sine theta. So the mg's cancel. So I get 9 cosine theta equals 16 sine theta, which gives me tangent of theta equals 9/16 if I divide by cosine of theta and 16. And now we can just do inverse tangent, and we'll find out what that minimum angle is. So I don't know if you remember, because it was last week sometime, but we did an example with the ladder leaning against the wall, and we had the person that was climbing up it. Do you remember that problem?
Yeah.
Kind of.
Vaguely, yeah.
That's exactly this.
Mm-hmm.
That's exactly this problem. Well, not exactly, because we had two forces that were pushing down. We had the weight of the person and the weight of the ladder. But it was really the same kind of thing, and we looked to see what kind of angle was necessary to keep this person from falling. And so it's a similar kind of problem. But anyway, there you go. That'll be the angle. That's the critical angle, basically. That if we get smaller than that, then this pencil is going to fall over. If we're bigger than that, then the pencil is definitely going to stay put.
So I have a question for you.
Sure.
I guess it doesn't matter now that I think about it, so never mind.
Those are my favorite kind of questions.
Well, the question was...
The ones that get answered before I have to say anything.
Yeah, because I was going to do tan inverse of 9 over 16. My calculator was in radians, and I got 0.51, so on.
Uh-huh.
And then I tried it in degrees and got 29.4.
Okay.
But I was like, which one's correct? Well, they're technically the same thing. Just
yeah, they're both correct
degrees.
as long as you write the one as degrees and the other as radians.
Yeah. Yeah.
The better one, of course, is the radian number.
Yeah, I figured.
Except we're in physics class, and in physics class, I guess degrees are acceptable, as much as it pains me. But. All right, so we better for number 70 here? Yeah, we good? Thumbs
Yeah.
up? Okay, so hopefully this helps with the homework. Again, it really just comes down to any of these equilibrium problems. There's two things you got to do. Balance out forces, balance out torques. And they're usually related because forces affect torques, right? So, and you'll notice that we kind of did that with, well, specifically the door one that was on the hinge. We used the torque, we calculated the torque and then used the torque to find the force, right? So those are in general how those go. And then the deformation stuff, it's always stress over strain. That's how you get moduli. So we're really looking at how much does it get affected by the given amount of force that's applied. But we always have to sort of normalize for the situation. That's why we take force per area. And the same thing with our deformation. We usually look at the change over the original. So we look at like a percent change. Because if I told you that I have a piece of metal and it increased in length by 1 centimeter, okay, was the original thing 10 meters long? Then I don't really care. Was the original thing 4 centimeters long? Then I really care, right? So just be aware that we definitely normalize it to the situation. All right, I'll tell you what, let's take a real quick break. Let's come back at about 10 after, and we'll dive back into gravity. We'll talk more about what's really going on with that. Eventually today, we'll even talk a little bit about black holes and why they're black. So anyway, so I'll be back in a little bit. You'll know I'm back when my video pops up as me again, but I'm gonna hit pause. All right, welcome back. So let's continue talking about gravity and how we can take this approach of this universal law and adjust what we already know about it. So we've already seen that gravity does change. It's not always the same. So like when we go with the 9.8 meters per second squared, that's valid on the surface of the Earth for the most part. Right? Obviously, it's going to vary a little bit depending upon where we are. Like if we're up on a high mountain, like if we're up on Mount Everest or something, we'll get a lower gravitational attraction than if we're down in Death Valley or something like that. We also saw that it depends where you are on the Earth, right? Whether you're at the equator or the pole, because the radii are a little different. But we did see that that gravity changes even more drastically as we change our location. So like we ran the numbers for being up at the International Space Station and we got 8 point something for the gravitational attraction due to the Earth as opposed to the 9.8, right? So it depends where we are. So obviously then we're gonna have to adjust how we look at other things. And what we're going to look at first is potential energy. Like how do we figure out gravitational potential energy if we don't let gravity be constant? Because what we've done before with the good old MGH, that requires constant gravity. And if you think about that, if we're going to go with h as the distance away that we've changed, our vertical distance, that vertical distance could be large enough that the gravity changes as well, right? So let's take that into account. But we're going to apply some physics. So let's go to the board. I have a feeling this is when the dog is going to go. All right. So let's go back to how gravity is defined. So we saw that the force due to gravity, we have that big G. That's the gravitational constant. We multiply that by mass 1 and mass 2. And then we divide by the square of the distance in between. So G is just a constant. It's the universal gravitational constant. Mass 1 and mass 2 are the masses of the two objects. And then R is how far apart their centers of masses are located. Okay, so there's the force. So now let's look at potential energy. And let's think about how we defined potential energy. Before, when we did the MGH, why was it MGH? Do you remember? You remember where that even came from?
Because if you're up high, you're going to have a higher potential energy due to gravity than you are saying just standing on the ground. That's where H came from. And then
Okay.
mg is just the act of gravity on you at a certain point in time.
Okay, so for sure, as you go higher, there's more energy available. And when we think about it, it was really, that was the extra energy that could get turned into kinetic energy. Yeah? So think about kinetic energy. What changes kinetic energy?
The velocity and the distance.
Okay,
Traveled.
so not necessarily.
Wait, no, not the velocity. Sorry, the velocity. It's the velocity squared. So.
Okay, so velocity.
I'm thinking of a different equation.
Yeah, so velocity will change your kinetic energy. So how about that? Where did the 1/2 mv squared come from?
Because it was the integral of something else. I forgot what it was specifically, but it.
Okay, you're right.
Oh, it was the integral of work, wasn't it?
It was the integral of work, yeah. So work, and this was I think it was called the work kinetic energy theorem. And work is really a measure of the change in kinetic energy. So if potential energy is basically storing energy to allow for kinetic, it's work. So this MGH was really looking at how much work is done by gravity. Because you remember your work is force times displacement. So if I've got this thing and I move it up, how much work got done? Well, it's going to be whatever force is being applied, which is the force due to gravity. That's our mg. And then we move a certain distance. That's our h. So that's where that even came from back in the day, was looking at the force, the work done by that force. Okay, well, we're going to approach this the same way. We want to look at what is the work done in moving an object a certain distance up according to this. Well, since this is now variable with position, we're going to have to integrate. So the work is going to be an integral from, I'm going to put here Ri to Rf. So from some initial position to some final position of this force, so we're going to have a G m1 times m2 over r squared dr. But the other thing I need to think about is how I have my r initial and my r final. Like if this is my Earth, or my whatever my object is, and I'm going to be some points out here, I'm going to say that this short one is r initial. So then the long one is going to be r final. So this is how I'm going to define locations that the center of mass of this object is actually going to be at 0. And as I move away, my r gets bigger. Okay, so we just need to define it some way. And I think this makes sense. Like if we're going to talk about the potential energy due to gravity with the Earth, we can maybe think about it as, well, I want to increase my height, increase my distance away. So this is actually still in line with MGH. So if I do it this way, then the force that's acting on my object is actually pulling towards the center, which makes this negative. So this is how we're going to calculate how much work is done. All right, so far so good? Thumbs up?
Yep.
Okay. So this is no different than how we did work before. We're just now assuming it's not constant. Well, the G, the M1 and the M2, we're going to treat those as all constants. That makes sense. G is a constant. And M1 and M2 are the two masses, so they should be the same. Those shouldn't be affected as I'm moving things. So we'll pull those out. And then I'm going to integrate -1 over r squared, which gives me 1 over r that I'm going to evaluate at r final and r initial. So we get G m1 m2 times 1 over r final minus 1 over r initial. And so here's the work done to move it from a lower initial position to a higher final position. Okay, so I'm just going to leave it like that for right now. All right, so that's the work done to go from position to position. So the potential energy then is the difference in these, right? It's the work done. It's getting stored as your initial, or as your potential energy. So really what it comes down to is this R initial, R final. But think about that as the H. Let me do some algebra real quick. So we get G M1 M2 times R1 minus, or sorry, Ri minus Rf divided by Rf times Ri. That got kind of small. Let me rewrite it up higher. But I want to show you how this pretty much is MGH when we go a short distance. So we've got this work is G M1 M2 times Ri minus Rf over Ri times R. And then let me actually rewrite it one more time. So we have G times M1 M2 over Ri times Rf times Ri minus Rf. So think about this. When we went to gravity is constant, that means that our Ri and our Rf are about the same distance, right? I mean, they're off. They're off by h, but they're pretty similar, very similar. So that means that this piece right here, that's pretty much just mg. That's the force due to gravity. If Ri and Rf are almost the same, then that's pretty much r squared. And then Ri minus Rf, that's Rh. So when we went with that assumption of the work done was mgh, or that's the change in potential energy, that was fine as long as those two r's were fairly close to each other. And for all the kinds of things that we did that, where we're moving a particle, 50 meters or something, that's totally fine when you compare it to the actual distance of r, right? That's the radius of the Earth, which is thousands of kilometers. So an extra 50 meters doesn't really matter. Anyway, the other thing that you may have caught and you didn't want to ask because you might have been a little nervous, you may have noticed that this Ri minus Rf, that should actually be negative because we're going further away than we were, which would mean that the work done by gravity is negative. But you guys should already know that. When I take an object and I lift it, gravity does negative work. I do positive work because it's going in the same direction. So it actually, everything does line up. It is totally fine. All right, so what that means is that if we want to extend this to a, let's not have gravity constant, we now have gravitational potential energy given by this formula. Is going to be U equals minus G M1 times M2 divided by R. That is what we got when we integrated. Obviously, I didn't put in my bounds because the work is the change in the potential energy. So it's this one minus the other one. So this is more appropriate for gravitational potential energy. It actually applies to things where we don't or can't keep gravity constant. All right, so a couple more things about this. I want you to think about what happens to this as R gets really big or gets really small. So again, here's our object. So the Earth, let's say, and we'll start at 0 and we'll work our way out. So let's start far, far away. So if we're in a galaxy a long, long time ago, far, far away, what's U gonna be?
This feels weird to say, but wouldn't it be really small because the radius is super big? And okay.
I know you are used to it being really big, but it would be really small, and in fact, it would be 0. Right? As R goes to infinity, U goes to 0. So the way that we've defined it here, potential energy becomes virtually 0 when you go really, really far away. All right, I know that doesn't feel very good, but does it make sense?
Because let's say we're super far away from Earth. We're super, super far away, like outside the solar system. Is Earth going to be pulling us in?
Probably not.
No. I mean, there is going to be a gravitational attraction, but it's going to be so minute that we wouldn't even notice it. So then there's no potential energy. It doesn't want to pull us in and create kinetic energy because we're so far away. So I know it feels weird, but it makes sense that there shouldn't be any potential energy. Okay, but what about as r goes towards 0?
It gets larger.
Okay, so this magnitude is going to get bigger because we're dividing by a smaller number, but it's negative. So u is going to approach negative infinity. So I want to be careful here because like Jacob just said, it gets larger. That's actually not true. It's getting smaller. It's getting a larger magnitude, but it's a smaller number. Because remember, negatives, those are smaller than 0. Okay. I know you don't like the idea of this negative infinity, but luckily, we're never actually at r equals 0. There's always going to be some distance between the centers of mass of objects because objects are not points. They actually have size. So we don't have to worry that r actually ever equals 0. So we'll always get a number, but it's going to get very big negative.
What does the negative imply here? Like, because it's like potential energy would be a... Oh, I'm confused.
No, that's a good question. And, you know, don't just dismiss it as you're confused, Jacob, because it's like this is a thing. But I want you to think about it. The way that we did potential energy first with the MGH, potential energy increased as we went away. Is that still the case if it's minus infinity at r, 0, and 0 at r equals infinity? Is it still getting bigger as we go this way? I know we don't like to think about it with negatives, but as negative numbers get smaller, the number itself is actually getting bigger. Think about the real number line. If we're over here at minus infinity and I start working towards 0, am I getting bigger? Yes.
Yes, yeah.
I am getting bigger. So it still matches. It still matches that if we're here at the surface of the Earth and we go up a little bit, our potential energy got bigger.
So the negative isn't really an indicator for direction, like it would be with a vector quantity? Okay.
Oh, well, and here's the other thing. Go back to when we calculated potential energy before with just MGH. Where did you set 0? Where did you set a height of 0?
At the ground level to whatever it was falling to.
Okay, so at the ground? Surface of the Earth?
Well, the surface, the distance between where it was going to be falling from and where it was going to be colliding. So it was usually the surface of the Earth, but it could be like the distance between a tabletop and your floor. So.
Okay, you just hit a key word where you said usually. And you're right, usually we made it the surface of the Earth was 0, but sometimes it was the surface of the table, or sometimes it was wherever. We could pick 0 wherever we wanted. I don't know if you remember that, but you could pick h equals 0 being anywhere you wanted, which means you are picking where potential energy is equal to 0. Sometimes you made it the floor, sometimes you made it the table, sometimes you made it the top of the roof, you know, whatever. You chose your 0. Well, that's what we're doing here. we're choosing 0 to be super far away. But it's still consistent. It's still consistent in that as we move closer to the center of the Earth, our potential energy is dropping. It's becoming more negative. So it's totally fine. Like it matches everything we've done before. It feels terribly wrong because we never talked about negative potential energy. But go back to those problems and set 0 at your tabletop. If the tabletop is, if this is 0 potential energy, if we go below it, we now have negative potential energy. We just usually designed it in such a way that 0 is where we stopped, so we didn't have to worry about going any further down. But there's nothing to stop us. We could have made 0 potential energy be at the top of Mount Everest. And then everything we ever would have done, we would have had negative potential energies. And the reason it didn't matter is because it was always the change. I just wanted to know what's the difference in these two. Because the difference in these potential energies was what could then be turned into kinetic energy as it dropped. Whether this is between 0 and 5, -2 and 3, -906 and -901, they're still always 5 apart, and that's what mattered. We just always chose our numbers so that we didn't have to deal with negatives. Well, the way that we're going to have to do it with these, because of how we define the force, it's going to make it that our potential energies are negative. But it's still going to be what's the difference in the potential energies that we care about. I know it hurts. I know your brains right now are like, nah. But it's completely consistent with what we've always done. And what we did before is a good assumption for small changes in R, even with how we define this thing right here. All right, so again, I know you don't like it. I know you don't like it, but this is how we're going to do it. And again, we don't actually have to worry about R equaling 0 because we're always going to be a little bit off depending upon how large our object is. Okay, so now that we've got this, I want to talk about escape velocity. Okay, real quick though, so Victor just says, so what can we consider a large R? That's going to depend. That's going to depend on the situation, what we're talking about. If we're talking about Earth, for example, in terms of a large enough R not to worry about gravity. Is that what you mean, Victor? Okay. So in terms of how far do we have to go before we can ignore gravity? I mean, obviously it drops to 0 when we go to infinity, but if we're 1,000,000 miles from the moon or from the Earth, is that enough? Are we, 1,000,000,000 miles? Are we a Google miles? It's like anything else in terms of how long we would consider it important. And it usually depends, if we're going to talk about Earth, it depends upon the other objects that also are pulling on us. So like if we're somewhere in the solar system, it's really the sun that's going to drive how far we go or how we're going to move, unless we get locally close to one of the other planets. Right. Second would be Jupiter. After Jupiter, and then Saturn, and so on. And so how far exactly, I can't give you a number. I can't tell you if R is at least this far, you can ignore the Earth. Because again, it's going to depend on what we're doing. But eventually, this gravitational force, I mean, what if that thing drops to, 10 to the -6 newtons? Are you going to care about that? Probably not. But would you care about 10 to the minus 5, 10 to the minus 4? At some point, the answer is going to turn into, yes, I do care about that. And that's really going to determine how far away you can go for it to matter. And Ian, yeah, we're about to cross over into Diffie Qs. In fact, you're going to get a little preview of what we're going to talk about on Wednesday. All right, so let's look at this as a, how fast do we have to go, say at the surface of the Earth, to actually get to the point where gravity of Earth isn't going to pull us back. Okay, so we call this escape velocity. And it really is what it sounds like. It's what velocity you need. So it's the needed velocity to, I'm going to say escape the gravity of an object. And I don't want to just say of Earth, because there is an escape velocity for Earth, but there's also an escape velocity for the moon, for the sun, for a black hole, right? It doesn't really matter, but whatever the object is, it's a velocity that you would need to give it a start such that that kinetic energy would be able to get you to that point where the potential energy drops to 0. Okay, so this is where we're going. This is what we're going to try to do. So let's look at this from an energy argument. So I'm going to go back to a flat Earth because I am a flat earther at heart. And let's look at, this is our initial. We'll do our initial. And then when we finally get up here, this is basically R equaling infinity. Well, we'll call it R final. Let's just call it R final. And let's look at the energy argument for this. So if we get to escape, basically, we're going to want to make it so that the kinetic energy here is 0. We're going to use all of our energy to overcome potential so that we get the kinetic there is equal to 0. Down on the ground, our kinetic energy is going to be 1/2 mv squared. Whatever velocity we end up giving it at the start, hopefully will kick us out. Okay, so then if we look at potential energies, the potential energies here, this is going to be minus G M1 M2 over R final. So that's what we found when we did the integral. And then down here, RU is going to be minus G M1 M2 over R initial. All right, so far so good. So now let's add them up. So initially, we've got 1/2 mv squared minus G M1 M2 over Ri. So that's our kinetic plus potential down at the bottom. Up at the top, we're going to have no kinetic energy. So it's going to be 0. And then we're going to add to that the potential energy up there, which is going to be minus G M1 M2 over R final. All right, so good. So now let's just do some algebra on that. And let's see what happens to this V. So I'm going to go ahead and move some stuff around. This mass, by the way, needs to be either mass 1 or mass 2. Let's call it M1. So that's the mass of the object that we're firing at. Mass 2, that's going to be the mass of the body that we're trying to escape. All right, so I'm going to divide everything by M1. That's just going to go away. I'm going to move some stuff around. So I get 1/2 V squared is going to equal G M2 over R initial minus G M2 over R final. So let's think about R final. If we actually want to get to the point where gravity no longer affects us, so we've got basically 0 potential energy, this is R final needs to go to infinity. Because we need to be able to just go flying away and never come back. So if RF goes towards infinity, this thing is just going to disappear. So we get 1/2 V squared equals GM2 over that RI. So I can multiply by 2 and then take a square root. And I'm going to drop the subscripts because we now only have one R and one M. So we get the square root of 2GM over R. And this is our escape velocity. So this is the velocity that you would have to impart in an object so that it could overcome the force due to gravity. And notice that it depends only on 2 things: the mass of the object and how big the object is. So as something gets larger mass, so if we've got a heavier object, then the escape velocity increases. Similarly, you'll increase your velocity if your radius decreases, keeping everything else constant. So think about the Earth with its mass. If we were to make it twice as large, then we'd double this radius, which is going to reduce this escape velocity. So it'd actually be easier to get away from the Earth if the Earth was larger size. If it was the same size but more mass, so we were denser, it would actually be more difficult to get away. All right, so if we wanted to, we could actually calculate the escape velocity for Earth. And let's do that. Real quick, one more thing. Notice this doesn't depend on the object itself. So if I want to send a like a space shuttle away from the Earth versus a baseball, it doesn't change the velocities necessary. I would need to impart the same amount of velocity whether I'm throwing a baseball so that it never comes back to Earth or launching a rocket. And that probably feels wrong because you think about what you have to do to get a rocket to go. Realize that when we send something out of the Earth's orbit, like we send something to the moon or Mars or something like that, we're not giving it all the velocity at the start. We keep applying force for a long time, right? You see those rockets burn for a while. So this would be more like we're firing a gun. So we're going to put the space capsule in a gun. We're going to fire that gun. How fast do we have to launch? I don't know if you guys have ever seen, there's that old silent film called like From the Earth to the Moon. It's a French film, and they basically fire a gun at the moon, and you see the scene where like the face in the moon gets hit by like a little bullet or something. Well, that's kind of what we're talking about. This is the velocity we'd have to impart. All right, so let's see what that would look like. So for Earth, all right, so I'm going to look these numbers up in a book because I've got a book that's got nice little numbers for all this stuff for us. Okay, so first of all, for the gravitational constant, that's always the same. That was that 6.67 times 10 to the minus 11. But then we have the mass of the Earth, and the mass of the Earth is 5.97 times 10 to 24. And that is in kilograms. And then we're going to divide by the radius of the Earth, which is 6.38 times 10 to the 6th. So just about 6,400 kilometers. Now, before we even calculate it, look at the order of magnitude here. So we've got minus 11 and 24, so that's 13. Divided by 6 is 7. So the square root of 10 to the 7th, we divide by 2. So that's 10 to the 3rd, 10 to the 4th. So we're going to get a number that's on the order of 10 to the 3rd or 10 to the 4th. So thousands, tens of thousands of meters per second. Well, let me crack out my trusty TI-89. Let's see what we get. All right, so the number I get is 11,173, we'll just round to the nearest, meters per second. So if you were able to take a baseball and throw it that fast, it would be able to escape Earth's gravity and just go flying through the universe forever. Ish. I'll explain the ish in a second. All right, so that would be for Earth. Let's change it to the sun. Now, obviously, we couldn't be on the surface of the sun because we would just burn up, right? But let's just say we could be on the sun. So for the sun, just so you know the numbers, the mass of the sun is 1.99 times 10 to the 30th. So on the order of 1,000,000 times more massive. And in terms of its radius, it's 6.96 times 10 to the 8th. So it's about 100 times more larger in terms of radius. Well, obviously, if you look at the numbers here, we're going to get something significantly larger. You just use the powers. Minus 11 plus 30 is 19. Minus 8 is 11. So now we're on the order of 10 to the 5th or 10 to the 6th. And let me just grab that real quick. Let's change my numbers on my calculator. All right, so my magical TI-89 says that for the sun, if we wanted to escape the surface of the sun, we need to go 6.2 times 10 to the 10 to the 5th meters per second. So that's like just about 620,000. So like 60 times the speed necessary to escape from Earth. So you can see how adjusting the mass and or the radius can affect your escape velocity. Okay, well, let me come back to the ish. Remember how I said if we threw it this fast, it could escape the Earth? The reason that that's not quite true is because of air resistance. As we throw that baseball up, the drag is going to slow it down. In fact, it's going to slow it down a huge amount. And so it would have to be much greater. But if we were like on the moon where there is no atmosphere, then that legit would be the velocity that we need. So the moon's is going to be smaller because it's a smaller mass and all that. And we could use this formula to calculate it. All right, so this is what we call escape velocity. Now, where this gets interesting is notice how this is already growing pretty big. Like for hours on Earth, we were 1.1 times 10 to the fourth. Now we're up to 6.2 times 10 to the fifth if it's the sun. Well, what if we kept getting more massive? Or more to the point, more dense? Eventually, this number, it's going to go up. It's going to become 10 to the sixth. Then it's going to become 10 to the seventh. Then it's going to come 10 to the eighth. And that's where it starts to get interesting. That's where it starts to get really interesting. Because what's the universal speed limit?
Light speed.
Okay, so we know that the max speed in the universe is the speed of light. Okay, well, I say no. It seems like that's how this is playing out. So we know that the maximum that anything can have in terms of velocity is 3 times 10 to the 8th meters per second, which is the speed of light. If you've not seen this, we use the letter C for that. Excuse me. All right, so there's our maximum velocity. So at some point, if we increase the density enough, our escape velocity is going to climb above 3 times 10 to the 8th. So what that means is that if you have an object that's that dense, is that nothing is able to escape its gravitational attraction. So if you're on the surface of that object, you'd never be able to leave. Well, that, my friends, is a black hole. So black holes are objects that are so massive, they're such that their escape velocity is greater than c. So not even light can get away because the light cannot travel fast enough to get away. So that's what's going on with a black hole. Now, we don't know for sure what's at the center of black holes, but we're pretty confident that they're like the cores of collapsed stars. So you have all that stellar material that has just shrunken down. I haven't changed the
Computer screen for a second. We'll come to this one. I bet you're tired of looking at the board. Okay, so when a sun or a star explodes, right, goes nova, the remaining stuff crumples in. And so you get this huge mass in a very small space. So it becomes very, very dense. And so we do know that this happens. We have seen this. And so it's not a huge assumption to say, well, could there be things that collapsed even further, became more dense? Well, so most likely what's at the center of a black hole is something that's super, super dense. A lot of mass in a very small, small volume. It's so dense that when things get close enough to it, they can't leave. They just get pulled in to that black hole. And so now all of a sudden, not even light escapes. So when we talk about seeing a black hole, that's kind of false. We don't see a black hole. What we see is the absence of light. There's no light there at all. And in fact, you'll usually see kind of a little bit of a ring around it, especially if a star strays too close to the black hole. Because what will end up happening is that black hole will start, sucking in pieces of that star. It'll kind of spiral around. And the bits that are beyond the point where the gravitational attraction is large enough to create this escape velocity of 3 times 10 to the 8, that stuff, the light is still coming out and we can see it. But as it moves closer and gravity gets stronger, eventually you get to the point where that escape velocity is too high, and now we don't see the light anymore. So that place where it terminates from being bright to dark, we call that the event horizon. And so that event horizon is the distance away such that gravity gives us just the amount of escape velocity that's equal to 3 times 10 to the 8th meters per second. So now think about what we can do. We can reverse engineer, right? If we can calculate the radius of this black hole, so we look at that event horizon and we see how big around it is, you can use that R with the gravitational constant and the V, the escape velocity, to get you a number for the mass of what's inside. So that's how we can actually figure out the mass in a black hole. So I don't know if you've ever wondered that, again, with there's no scale big enough. Never mind the fact that we could never read the scale because the light would never come off of it. But we can actually use this calculation and just go backwards. Given an escape velocity of light, a size of our black hole, we know how much mass is actually in it. Now, how much space that mass actually takes in, we don't know, right? Like, so we might have this black hole that's like a solar system across in radius, and all that mass could fit in my house. I mean, I don't know. I don't know how dense it is, but we do know how much mass is in there. So kind of crazy that all we're talking about here is a simple little rule of how things attract each other. And the next thing you know, where you're finding things in our or in our universe that are so massive that nothing can escape it. So Victor, if there were intelligent life in a massive planet, they'll need a lot more resources to escape their planet. Yes, for sure. So if if you lived on a larger planet, it would be more difficult to escape, or it would require more energy. Let's put it that way. Let's not go to difficult. It would require more energy to escape the gravitational attraction of that planet. So if we lived on, say, Jupiter, for example, then it would be much more difficult. We'd have to spend a lot more energy to get off of that planet. So when you say you need a lot more resources, I think that's very accurate. You'd need to be able to construct things in such a way that you could provide that energy in some manner to get beyond. So, I started to say more difficult. Well, in our experience with what we know and how we construct things, yeah, it would be more difficult to design something to be able to escape, but not impossible to a point, right? There might be a point at which we get something that's where the gravitational attraction, everything is so massive that velocity, escape velocity, increases enough that it would be too difficult for us to actually make it happen. But yeah, so a bigger planet would be more difficult to come from. So clearly all the aliens that visit us then must come from small planets because it's easy for them to actually get here. I'm being completely facetious, by the way. Because if any life actually comes and visits us, like if we have been visited by alien life, they have to be able to do things that we cannot do in order to go the distances that we're talking about and the energy expenditures, because with what we have and our knowledge, it would not be possible to really go those kinds of distances in any sort of reasonable amount of time, right? But we also don't really know if we can go through wormholes. We don't know if they actually do what we think they do and all that. So I think there's a lot to this universe we don't know. But I personally don't think we've been visited by extraterrestrials. I definitely believe that there's intelligent life somewhere else in the universe. Just the odds, if you just go probabilities, they've got to be. But them visiting us, that's a whole nother story. But I might be wrong. Anyway, so there's a little bit about escape velocity and another thing that we see with gravity.
Question for you.
Sure, go for it.
So it's theorized that in the center of galaxies there's supermassive black holes.
Correct.
And I asked Kathy, I think last quarter, how would those black holes form? And she said she has no idea. Do you have an idea on how that's possible? Because if they're that massive, then it's probably not collapsing stars.
Right. It's possibly even more like a collapsing galaxy, or something like that. But I don't know. I'm not a cosmologist, so I don't actually know. But they would have to be really massive to exert forces that are felt the distances they're felt. You know, because like when you look at the Milky Way galaxy, for example, it's so humongous. I mean, like huge that we're talking about monstrous R's. And you've already seen that gravity, it decays with the square of R. So like if you multiply R by 10, you decrease your gravity by 100, right? So in order to affect things that far away, they do have to be incredibly massive. But I don't know what the mechanism would be. I don't even know what the theory is for what the mechanism is that would create such a thing. So I bet you could find it if you research, but I don't know off the top of my head.
Could it be like a black hole that like was formed from a collapsing star and then consumed other stellar masses or planets or whatever?
Oh, absolutely. And it could be black holes that merge. Like that happens. Black holes do come together and they attract each other, and then they merge. Like remember a couple of years ago when they found evidence of gravity waves? That was actually from two black holes that were coming together. And so basically when they collapsed onto each other, they produced this ripple that was so incredibly large that we were able to catch it. So it could be that too, where there were a series of collapsed stars that all kind of came together and then collapsed onto each other. So that I would definitely not rule that out.
I also actually had an additional question that's kind of related to all this black hole stuff and supernovas and stuff.
Sure, go for it.
What you mentioned earlier, how like during the last few seconds of a star's life, all of its mantle, all of its mass, most of it gets like sucked towards the center, and that would increase the gravity, right? Like the surface gravity, or
yes.
Yeah, so it would increase the surface gravity, but then a supernova occurs after that, from what I understand. So how does an increase in surface gravity cause an expansion outward, like through an explosion?
Okay, well, it's exactly that. It's an explosion. The material. So this is now like atomic physics, because what will happen is. Okay, in a sun or a star, you've got hydrogens primarily, and then you got some heliums and stuff, and they will, they'll fuse together through nuclear fusion to produce larger things. And in the process of fusion, they release energy, just like fission also releases energy. So think now you've got all this stuff that's getting closer and closer together. It's getting more compact. They're starting to fuse. And each of those fusions creates a certain amount of energy. So if you've got trillions of these fusion events, you have this huge increase in energy. And one of the things that will happen with that energy is it will just end up pushing all that stuff away from each other. It basically imparts kinetic energy into all the different particles, and they go flying away. So that's how that condensing can then lead to ejecting. But it's not everything. It's not everything gets ejected, right? Just some of the material does. Because obviously if everything got ejected,
then there wouldn't be any neutron stars or black holes.
There wouldn't be anything left to suck you back in.
Yeah.
Right? And then you wouldn't have any kind of a mass there. So it's not everything. But when something goes, it does eject a lot of material. And a lot of that material is way bigger than hydrogens.
Yeah.
Right? Like everything that makes you up, all of the elements that make you up were formed in stars at some point. And to form things that are heavy, like irons and things that are even further down in the periodic table, that's a lot of fusion that has to happen. A lot of energy has to be used to do that. But yeah, as the saying goes, we are stardust. We are made up of remnants of dead stars.
So it's like an extreme version of like the fusion pressure that's present in like a live star, essentially. It's
absolutely.
Like a ton of energy being released. Okay.
Yep.
That makes sense.
Yeah, and in fact, we use that, like there are fusion bombs that use kind of the same idea. You just get stuff condensed enough that they react, and then that reaction is causes the release in energy, which then makes the explosion.
That makes sense. Thank you very much.
Yeah, you're welcome. Anyway, other questions about stuff I don't really know about, but I'm good at bullshitting?
Yeah, I got one.
Yeah.
So it takes time for us to see other stars because they're far away, and it takes time for the light to travel to us.
Correct.
Is gravity constant in the sense that it doesn't take time for it to affect us?
Okay, that's actually a very good question. Is there like a time lag with the gravity?
Yeah.
And my answer to that is I don't know. And I don't know that we know exactly the mechanism for gravity. So whether or not it's an instantaneous thing or there really is a time lag, because you're right. Like when you see sunlight, like if you were to go look at the sun, don't go look at the sun. But if you were to go look at the sun, that light you're seeing left the sun over 8 minutes ago. Okay, it takes a little over 8 minutes for light to get from the sun to the earth. You go and you look at other stars, they're so much further away that, like the closest star, the ones that Proxima Centauri, I think it's on the order of 3 light years away, which means that the light we see in that star left that star 3 years ago. So you're looking in the past when you're looking at stars. Some of the stars you see no longer exist. We just haven't seen the end of their life yet because we're seeing back in their history. So kind of a cool thing is a little bit off topic, but it's kind of a cool thing I think about when we're using like the Hubble Space Telescope and things like that to see further away, is that what we're really doing is we're looking further back in time. And I think that is really cool. Like for us in the history of the universe, a really good telescope is a time machine. It's letting you look back in the past at what used to be. Because the further away that object is, the longer that light has been traveling, which means the image that you're seeing was produced longer ago. So it's kind of a trippy way to think about it. But every time you look at one of those pictures from the Hubble, just think about that. Be like, we're looking back in time. We're looking back at what the universe used to look like. Anyway, so let me get back to Bradley's question. So yeah, when we just optically see things, or not even optically, like if we're reading, X-rays or, whatever else, gamma rays, they still are limited by traveling at the speed of light. So are we limited by that? I don't know. Because we also know there are things that are not limited by the speed of light. Just hold that here a second. So it's called quantum entanglement. And what you can do is you can take a particle and break it into two identical particles that have that are kind of related to each other. And what happens because of conservation laws, you can affect one of them, and that causes the other one to kind of follow suit, right? I mean, like we've talked about conservation of momentum and angular momentum and stuff like that. So think about in a closed system, if I were to have the momentum of this thing change, the other one has to change as well, right? So there's some conservation laws that kind of work like this. And what'll happen then is if object A, say the one that's in my right hand, if object A gets affected, then object B feels it. And what we've seen is that, and this has been seen, like we've produced this in labs, humans have experienced this. We've seen that when object A gets affected, object B gets affected instantaneously. There isn't it's faster than it would have taken the speed of light to go from point A to point B. So there are mechanisms for that already that we know exist. My hunch, and this is hunch, my hunch is that gravity works kind of the same way, that there's some mechanism that we haven't seen, that we don't know, that makes it so that it is instantaneous, but I don't know the answer for sure.
I like that answer. Thank you.
Yeah, you're welcome. I mean, the thing about so much of this and just physics in general is the questions never end, right? And every time we answer something or we think we get the answer to something, there's something else that pops out. And so I find that really kind of cool. I like the fact that there are questions that we don't have answered. I mean, I like it and I don't like it. Like, I would love to be able to be the one that sees the interconnectedness of everything and then could be, you know, it's like, oh yeah, here's just how the universe works. Like, I think that would be awesome. I just don't know if it exists because we keep finding out so much that is sort of like behind the scenes. And this actually brings up something that one of my students in trig asked me today. And I think she was kind of being facetious, but she said something, well, as soon as I tell you what she asked, you'll understand why I ran with it. But we were talking about the graphs of the trig functions, you know, and you guys remember how like sine and cosine, they're really related to the graphs of secant and cosecant with like the smiles and frowns hitting the peaks and troughs and all that. And so she said something like, well, do you think maybe the fabric of the universe makes it so that, you know, different dimensions, sine looks like secant or whatever. And so of course I went with this a little bit because I think there is a little bit of truth to that, you know, there is stuff behind the curtain. We just can't see behind the curtain. And so I think that a lot of what happens is based on perspective anyway. Like this we know, like if you talk about relativity, it's all about perception depending upon, you know, which reference frame you're in. I think for sure that there's some of that we just don't see it. So you take things that are kind of fringe, almost pseudoscience, like ghosts or ESP or things like that. I'm actually a believer that that stuff actually does exist, and certain people can kind of see it better, just like we all have different eyesight, just like we all have different hearing, just like we all have different whatever. I think there are some people that are more in tune with certain things in the universe, and so maybe can get a real quick glimpse of what's going to happen in the future, right? Those people that they know an earthquake's coming for some reason, right? Like you've heard about those people that they take down the picture frames on their walls because they're certain something's going to happen, and within an hour there's an earthquake or something like that, right? I think those people are just really in tune with whatever that is in the universe that makes them see that. So yeah, anyway, that's me, but that's me personally, you know, and I think that's how I try to make sense of the fact that there are some really weird ass things in the universe that we can't explain with the system as we've built it. And I'm an axiomatic guy. I like if then, right? If this is true, then the next thing is true, then the next thing is true, and so on. That's why I love math. That's why I love physics, because it really is. It's like one thing leads to the next, leads to the next, leads to the next. So when I'm presented with things that are kind of not there, obviously I have to wrestle with it a little bit. You know, and this is where things like religion and philosophy and all that come up, right? We as humans are trying to explain our place in the universe and all that. And I think for me, it's sort of I stick with the science, but but the science has aspects to it that we haven't figured out yet, or that we just are not capable of seeing, right? Like, I don't know if you've ever read the book Flatland or heard of it, but Flatland's a story. It's a short story. It's like a novelette about two-dimensional creatures. They live in flatland, so they're 2D. And I think about that a lot, that a two-dimensional creature would have no idea what 3 dimensions is like because they've never experienced it. You put them here and they'd be like, what the heck, you know? If you've ever seen that Simpsons Treehouse of Horror where they 3D Homer, bring him into our world, you know, he's walking around, he's like, oh my God, I don't know what this is. That would be the experience for us if we were to go to a higher dimension. So we're trapped in 3D world. It's our only experience. And so being able to look beyond that, I don't know if it's even really possible. So that's kind of where I let those things lie, is I put them into the, well, this is the part of the universe that I'm not privy to, that I don't get to see, you know. And I know that other people, when they're confronted with that, they turn to religion, right? I mean, you think about like the all-knowing God. Okay, you put your faith into that as that's the answer to all those things that we don't understand, right? Or whatever. But anyway, I feel like I've really digressed, but you guys are finding out an awful lot about me.
One last digression. The Flatland movie is actually free on YouTube if anybody wanted to watch it.
There's a movie called Flatland?
Yeah, there's a movie based on the book.
Oh, I had no idea. I'll have to check that out. Because I know you can also,
it's free on YouTube.
You can find the book an open resource. I know that it's pretty prevalent around, but it's kind of an interesting read. They have a class society. The more round you are, the higher you are in terms of your caste. So, you know, triangles, they're the brute force. They're like the military.
And lines are females, and they always have to talk because they're too dangerous.
Yep. Yeah. Because otherwise you can't see them, right? Because if a line's coming at you, you don't see it. So yeah, it's also got some good social commentary for sure.
Yeah, it's a great book. Yeah.
All right. So yeah, the only other thing I was going to talk about really with gravity, but I'm not really feeling it right now, is just how like if you got an object in orbit, you know, it's all being driven by gravity. And I kind of hinted at it last time, that you're just sort of perpetually falling, that it's the gravity that's causing that centripetal acceleration that allows you to continue to go in a circle. And so really you can think of orbits as their projectile motion. Like if I were to fire something, right? Like if I were to throw a baseball, that baseball is eventually going to come and drop down, right? And we know that it follows a parabolic path in the absence of gravity or air resistance. So let's say we're doing this on the moon or whatever. So if I launch something horizontally, it's going to fall like a parabola. But if I give it enough velocity, it's not going to fall. it's going to continue as gravity pulls it. It's going to keep moving fast enough that it ends up going in a circle. So you can really think about orbit as we've increased the horizontal velocity enough that we're not falling like a parabola anymore. If we were to still go further, we now are going to escape the pull of Earth, right? So it is kind of interesting how this dance works. And when we put things in orbit, remember that the velocity is definitely related to the radius. So the speed of an object ends up getting slower as we send it further away. So this is an interesting thing that I remembered hearing from one of the astronauts that was talking about trying to rendezvous. So you've got your two craft and you're trying to rendezvous. So let's say we've got craft number 1 up here, the one that's got my pen. So my pen is the one we're trying to catch, and we're down here. If I want to catch that thing, if I try to go out to its orbit, I'm going to slow down, and so I'm not going to actually catch it. And so to catch it, I have to come down so I can speed up and kind of get past it a bit, so that then as I pull myself up out, I can get it. And I don't remember who it was. I think it might have been Neil Armstrong, because I think he was part of that first group that did the first rendezvous of Gemini. And he said it was completely counter to what they did flying planes. So they actually had to go the opposite direction to speed up, which was counter to what they thought. And I just find that incredibly interesting, that as soon as you get away from air resistance, it's a completely different world. So anyway, but I think I'm going to stop here. We'll call it a day for today. But gravity is kind of cool, I think. Anyway, so what we're going to do on Wednesday is I'll answer any kind of last things about gravity. I'll make sure that there's nothing else important that I wanted to mention. And then we're going to go to fluids. And I'll give you sort of the brief important bits of fluids, because we can't just live in the gravity and fluids world. We definitely need to kind of move along. But fluids are pretty interesting in terms of what they do. And you guys know my background. I definitely dig them a lot. But we'll talk about why that that styrofoam cup got squashed down. We'll talk about why airplanes can fly. We'll talk about why you float in water and stuff like that. So we'll answer a lot of those questions. And then we'll finally wrap up the stuff that you missed from last quarter. So I think it's kind of interesting that we're a third of the way into this quarter and we're still finishing up last quarter. But hey, it is what it is. And we'll keep moving just in this direction. So any last minute questions? I'm actually going to go ahead and pause the recording